Let's set here as and switch 5, not this one. This, okay. Streaming should be up, and let's share this here. Han-Hsuan. Okay, hopefully everyone see the screen. Okay, cool. Okay, let's get started. So let's get back from the midterm to our teaching. Yeah, we have lots of material to cover before we get to final, and so we will try to be a bit faster now. I think we will skip some of the more detailed derivation to hopefully cover more material. Anyway, so we are done with midterm 2, and let's get back to our discrete Fourier transform. And okay, so as a reminder, we were talking about this discrete Fourier transform. We have some signal, and we will discrete signal, and we will transform it to its Fourier transform in a frequency domain is big X of e to j omega, which is going to be periodic with period 2y. Periodic with period 2 pi. And we have all sorts of property like linearity, multiplication, differentiation. We cover all this. So, and yeah, and as always, we have those conjugation properties, even odd and possible relationship, which we just get through in midterm. Well, they are for different form of Fourier transform, but it's very similar. And here are some of the Fourier transform pairs. Well, it's mostly Fourier series. Okay. And more interesting are probably this. So if you have an exponential decay function, then it's Fourier transform. Actually, you don't need to be exponential decay because it's discrete time. Wait. Yeah, I think you need to be the exponential decay. Yeah, this is exponential decay function. So yeah, the absolute value of a is less than 1. Then you transform to this kind of rational function of e to the minus j omega. Yeah. And yeah, so that was before midterm, I believe. Yeah, we have covered this convolution. It's quite interesting. You can cut off, to do this periodic convolution, you cut off just one period of your first function, then you convolve with the second function. You got this periodic signal as output. Okay. And then let's go back to the next topic of duality. So duality of Fourier series, Fourier transform, discrete Fourier transform. Okay. And so duality, first we have a review. So the duality we talk about in the chapter 4 is duality for the continuous time Fourier transform. And it's just something we noticed that the Fourier transform equation for the continuous time is the transform and the inverse transform has very similar formula or a very similar equation. So if we have one function and another function being transform pair, we kind of just switch t and omega here, and they will also become a transform pair. Oh, it's a little more complicated as you need to get a negative sign somewhere. But you can see that square wave function in time domain is transformed to a sinc function in frequency domain, then you can kind of reverse the role. Then you put a sinc function in the time domain, it will transform to a block function in the frequency domain. Okay. So now we want to get this kind of duality also in our discrete time Fourier transform. And we see that it's not quite possible because the two functions are very different. One of them is the continuous time function, and another is a discrete time function. So you cannot just sweep them and run and get another discrete time Fourier transform pair. Okay. So that's very annoying, but so kind of a spoiler, we already have this spoiler at the very beginning. So we cannot have a duality in this part by itself, but we're going to have it in duality with the continuous time Fourier series. And but before we go that, we look at the duality on this discrete time Fourier series first. So we could have talked about this in chapter 3, but somehow we decided to talk it here. Okay. Yeah, so let's go through the duality here. So in chapter 4, we talk about duality here because this equation looks really like this equation, just have a minus sign and they swap x and the big X. And similarly for this equation and this equation, they also look very similar. See, it's the same summation. You just have different normalization. It's not a big problem. So one word here and no one word here. And if you think this AK as a function of AK, so just instead of writing AK, you can write a sub k, you can write a bracket k. And now AK is the function of k. Then you will see that this equation and this equation are very similar. Just change a different minus sign here and you swap x and a. Okay. So for discrete time Fourier series, you actually have a very strong duality between them. And here is the high definition version of those two equations. Our synthesis equation for discrete time Fourier series and analysis equation for discrete time Fourier series. Okay. And yeah, you see they are very symmetric. So x of n is periodic with period big N, then AK also has period big N. Okay. And now we derive a more detailed duality is this. So if your G of n has Fourier series of coefficient fk, which we write as a function of k, so it's f bracket k, then you can put f bracket k as the input signal, so you turn k to n. Then its Fourier coefficients will be 1 over n g of minus k. Okay. So you can put this here, then this will get here with a minus sign and 1 over big N. And the derivation is pretty straightforward. You do a substitute of variables. So yeah, we start with jk, g and f being a Fourier series pair or discrete time Fourier transform pair with each other. Then we use this analysis equation, right? So because AK is going to be 1 over xn minus jk 2 pi over n, then you just plug in this here and just put in slots. So now AK is fk and xn is gn and everything else is here. Now we do a change of variable. So we're trying to get this equation to this equation. And so we swap k to n, but get the minus sign here. So swap k to n, so this k to n and this k to n and n to minus k. So n to minus k, so you cancel this minus sign, and n to minus k, n to minus k. Now we just change things a little bit. So obviously you can put the 1 over inside the summation. And another thing we change is this summation minus n bracket k is equal to summation plus k bracket n, because if you go yeah, because it's periodic, and if you go in negative k direction for n step, it's then also going to positive n k direction in n steps. Okay, you just have n consecutive k anyway. So the two summations are equal, and now we have this equation, and now this looks like a synthesis equation. Okay, so you compare this to a synthesis equation, you see that if you group this whole 1/n of minus k together as ak, then that's the synthesis equation between fk and this whole thing, right? Everything else match. So fk is the Fourier transform pair with 1/n of minus k as we can. Okay. So that's the duality on discreta and Fourier series. So any question? Pretty straightforward. Revision. Just to switch or change your variable. Okay. And if not, and let's see an example. I don't think it's too much happening here. Basically, just our favorite square wave function, and you see the duality. Okay, so square wave function duality. So we have a discrete signal. Once again, it's a square wave, and it's a square wave with 5 spikes because the absolute value is less than 2. So like from -2 to +2 is 1, and all others are 0. And the Fourier transform this wave calculated is sine over sine, and it's something periodic with period n equal to 9. Oh, sorry. So this thing is okay. Yeah, this thing is a little more complicated. So it's a square wave with 5 spikes, but it's also periodic with n equal to 9. Okay, so this will have a square with length 5, and it will repeat every 9 length of 9. But anyway, so it's a periodic square wave, and you do Fourier transform, and it's also periodic with period of 9, and it's this sine over sine function. And then from the relation here, we can pull this as our input signal. Those are our time domain signal. Not quite input, is the time domain and frequency domain. Then we can see the frequency domain will get to just plug in the formula 1/n minus k. So this thing divided by 9. And the minus k doesn't do anything because it's an even function. Okay. And those two functions are also going to be a Fourier transform pair. Any question? I think this is pretty straightforward. So this is the duality for discrete Fourier series, and also you can have the duality in properties. So seen here, we have kind of already seen this. So the time shift, you will get the time shift property. You get the extra complex exponential, and you can also have frequency shift property, and get another complex exponential, but with plus sign. And also the convolution in time gives you multiplication in frequency, and multiplication in time gives you the convolution in frequency. Okay. So all those are also symmetric because those two equations are very symmetric to each other, all these two equations. Okay. And okay, now finally back to this thing. So chapter 5 for the discrete and Fourier transform, what kind of duality we get. And it's really not something too nice, so we kind of finished it in this one slide. And with another example next slide. So it's going, as we already shown here, it's going to be dual to the continuous time Fourier series. Okay, so we have kind of a review here. So continuous time Fourier series, the two equations look like this. Somehow we are in reversal order here, but it's okay. So the Fourier series coefficients have this integral equation, and the signal has this synthesis equation. It's the sum of complex exponential. And we compare to the chapter 5 equation we have, where we have the Fourier transform is the sum of your signal times complex exponential and your synthesis equation, and just like this. Your synthesis equation is this 1 over 2 pi and the integral of your Fourier transform times the complex exponential in one period. Okay? So those two set of equations are really similar, so you can change from here to here by doing a change of variable. And also you need to think ak as a bracket k. Okay? So you change k to -n and omega naught t to omega, then you will change this equation to this equation. But instead of x of n here, you get a of -n, and you have small x of omega. Although you think small x omega equal to big X of e to the j omega. It's a little weird if you don't. Yeah. Yeah, this e to the j omega is a little weird, but just think the whole thing as a function of omega now, for now. And also you can change this equation to this equation by doing a very similar swap. So you also do change k to -n, but now we have a little more condition, because remember for the frequency for this big X function, we've talked about this many times, that big X has a period of 2 pi. But for the continuous time periodic signal, the period here can be anything. So this duality only works when your signal has a period of 2 pi. But it's kind of just why it is like this. You can think a little more about yourself, about why this has less freedom, but for now, you just need to remember that this duality only works when your period is 2 pi. Because if your period is not 2 pi, then you need to kind of scale your function. But if the period is 2 pi, and then I will set omega equal to 0. And so from here you want omega naught t equal to omega. But if omega naught is already 0, then I just t go to omega. Okay, so t equals to omega, and and as k goes to -n. So you can also change this equation to this equation, but you'll get the a of -n here. And then we finish with the example. So we change from a continuous time signal and its Fourier series pair to the discrete time signal and its Fourier transform pair. So we have a continuous time signal, and as we say, you need to have period 2 pi. So we just assume it has period 2 pi. And once again, it's a square wave function. And its Fourier transform is going to be the sinc function. A square function changed to sinc function. Someone, yeah. Yeah. And as we said, we can pull this function or this sinc function. Or discrete time sinc function, because it only sample one point of k, and pull this as the discrete signal, and also assume this big T1 as pi over 2 just because. And then you can pull this thing as as we will see that this thing will become your Fourier transform here. So it's basically the same, but there is something we skipped. That is, it was instead of a of k, you should be instead of a of n, you should be a of -n. But this a of k is even function, so these two are the same. For more general thing, you should get x of -n here. Okay. So any question on this duality between discrete time Fourier transform and the continuous time Fourier series? I think this is the most duality we can talk about here. Oh, someone is coming in. Okay. Anyway. Okay, another duality. Okay, so finally, in the last topic here, and you probably expected is we are going to solve some difference equation. And once again, this is very similar to continuous time. You do Fourier transform, so you have our constant coefficient difference equation for LTI system, and it has this form. Then so the difference equation has this form, and you apply Fourier transform on both sides. So you get some big Y and this weird time delay now becomes complex exponential. So it's e to the jk omega, e to the jk omega. And yeah. And then you can group them together. You can pull all the big Y and big X, pull them together. And remember, for LTI system, you have big Y equal to big X times big H. This is also true for discrete time system because of the convolution property. Okay. And yeah, so you pull things around, then just similar to the continuous time case, you can run down this H directly by reading the coefficient in your difference equation. So it's going to be this sum bk equal to minus jk omega divided by sum ak equal to minus jk omega. And yeah, it's a little different from the continuous time case. Continuous time case, you have j omega here, j omega here, j omega to k, j omega to k, but you have e to the minus jk omega. That's the different the discrete time system function again. But how you deal with this is very similar because, well, let's just see an example. So in example, we have a difference equation here. So y minus some y over n minus 1 plus some of n minus 2 equal to x over n. And you can just read the system equation from here. You have a 2 here divided by 1 minus, and it's minus 3 over 4 equal to minus j omega plus 1 way and e minus j2 omega. Okay. And e to the minus j2 omega is obviously the square of e to the minus j omega. And we have good number here, so we can factorize the lower part. And it's a 1 over 2 and 1 over 4. And once again, you can do this partial fraction expansion. You view this e to the minus j omega as an x and do some big variable x, and you think this as a partial fraction expansion. And so assuming we don't do the calculation wrong, then you get a 4 and 2 here. Then you just look up a table and do the reverse Fourier transform of this thing to get the US small h. And reverse Fourier transform of this 1 over 1 minus a e to the minus j omega is a to the n u of n. Okay, don't forget the u of n. And anyway, so you will get some exponential decay here. And yeah, hopefully your system is set up nicely, and you will get something convergent. And so this h will be less than 1, and you will get something exponential decay. Okay. And yeah. And so this goes Fourier transform to this 1 over 2 to the n, and this goes to this 1 over 2 to the n. So difference of 2 exponential decay. Just very similar to the continuous time case. So any question on this? No. Okay. And then yeah, and just as what we want to do. So now you have the system function. You can also compute some input-output pair, and we give easy input. So we have input also exponential decay because we want some rational function in e to the minus j omega. And so first we can compute the Fourier transform of the output. So big H times big X, and the rational function times rational function get another rational function. And then you can do this partial fraction expansion. But now it's more complicated because you have some root that some factor that is square here. So you will need a square term and a not square term. And you will need to solve for those three coefficients, which we skip the solving. And then once again, you do the inverse Fourier transform by just look at the table. So those two terms are going to be the exponential decay, and this term is exponential decay times another polynomial because you look up table and you found out that you have square here, you get extra n plus 1 here. Question? No. Okay, then that's chapter 5. And yeah, chapter 5 is we do discrete time Fourier transform. It's very similar to continuous time Fourier transform, but but the important thing to remember here is that in a frequency domain, so for discrete time signal, it always has period 2 pi. Okay. Something you need to remember in your outside class. For discrete time signal, the frequency domain signal always has period 2 pi. Okay. And then we will have, I didn't time this. Okay. So we'll post this more formally later, but you will have homework 5, and let's also have this due in 1.5 weeks. Be okay? Okay, any question? Maybe I will shave out some question because we are a little tight on schedule. Let's see. Okay. Anyway, chapter 5. We will think about the homework problems later. Let's see. We are okay. Yeah, we also do this on chapter 3, I think. It should be okay. And we are on May 20, and let's have this due on May 30. Yeah. And maybe we'll cut out some problem. Okay, no question. Then let's go to. Okay, now let's have a fun part. Let's time jump to chapter 9. Okay. Let's see, chapter 9, and I need to change these to this. Okay. And share screen. Oh, this thing. Let's see. Everything okay? Okay, looks okay. Okay, chapter 9, Laplace transform. Now, this chapter we are going to, so we jump from chapter 5 to chapter 9, so we skip 6, 7, 8. There are lots of interesting applications of Fourier transform in those chapters, and like modulation, stability, filters. But we skip them because we want to talk about more fundamental mathematical part. And those topics are pretty interesting, so you can look up the book if you have time. But anyway, so now we go to Laplace transform. And now this chapter is pretty mathematical. We are going to do some complex analysis. We are going to use a lot of concept in complex analysis, but we are not talking about complex. But we are not really teaching about complex analysis, so it will be kind of ad hoc in lots of points. But it's also useful in analyze. It's also still very useful for tell you about analyzing the properties like of your system, like stability and causality. We are going to see this. And yeah, it's quite interesting. Although it's quite more mathematic. So Laplace transform. So this is the this is the dictionary syllabus of what we are going in this chapter. Quite a lot of things. So I guess let's jump right into it. So Laplace transform. Well, the starting idea is kind of we want to generalize Fourier transform to complex frequency. Okay? And so we kind of start this back all the way back to chapter 3. And I remember in chapter 3, so this is the motivation of we doing Fourier transform back in chapter 3 is that we found out complex exponential, so some function of the form e to the st for any complex number s, it is eigenfunction of an LTI system. So your output will be some eigenvalue times your complex exponential. And we found out that we can compute this eigenfunction h of big S from your impulse response small h of t by this equation, integral minus infinity to infinity h of t e to the minus st dt. And yeah, and at that time, this S we didn't have any specification. It can be anything. So those two equations are true for any S, right? S can be any complex number. But then in chapter 4, we think that maybe maybe we want to look at purely imaginary S, so we have those complex exponentials because they are quite nice. And when we restrict S to complex exponentials, we restrict S to purely imaginary numbers, then you get the Fourier transform out of this. That's why we always write h of j omega. But now we want to go back to full generality. Okay, so we won't consider this h of s for any kind of s, any kind of complex s. And then that will give you exactly this Laplace transform. So at least one of the form, but this is the most standard form that everyone uses. Okay, the bilateral form, but it's also kind of standard. So when we don't specify it, we are thinking about the bilateral form. And anyway, so we can define the Laplace transform of a function like this. So just your input function, then you transform x of t, then you transform it to the frequency domain, and you become some big x of s. And this is really a generalization of Fourier transform because it used to be s need to be a purely imaginary number. That's why you run j omega here. But now s can be any complex number. Okay. So any question about the definition? Now it's it's like a very kind of a straightforward how should I say? Straightforward generalization of Fourier transform. And this is kind of a thing you want to do in complex analysis. That is, your function depends on real variable, and you just extended it to the whole complex plane. So it's a little weird. You have a function defined on purely imaginary variable, and now you extend it to the whole complex plane, and then some bad things happen with convergence, and you get some analysis around it, and you find an interesting property, which is what we are going to see. Okay. Anyway, so that's the forward direction of Laplace transform, and even though we haven't seen the reverse direction, we don't even know whether the reverse relation is possible, but we believe that those two functions are going to form a transform pair. So we write it in this way. So we say some function x of t will form a Laplace transform with some function big X of s. Okay. And also we are going to analyze this. Oh, I forgot to wait. Can you see? Oh, you can see the cursor. Okay, but I should still. Okay, let's change to the. Okay, this is better. Yeah. So x of t form Laplace transform vector to big X, and we are going to analyze this by breaking S equal to the real part and imaginary part. This is nice because then we can reuse what we know about Fourier transform. Because remember, when sigma equals 0, then this is just a Fourier transform. So if x is just some purely imaginary j omega, then this Laplace transform just go back to Fourier transform. Something important to remember. Okay? Yeah, just as we say, s equal to j omega, then you put everything to omega, and then you find out that this become e to the minus j omega t, and this is exactly the analysis equation of Fourier transform. And then you figure out that why I always write the Fourier transform with this big weird j omega here, because we are actually thinking about Laplace transform is purely imaginary s. Okay, so x of big j omega here. And yeah, so just this effect we write in another equation. Find out this is the Fourier transform of x of t, and this is your Laplace transform condition on your s being some purely imaginary number. And now even more interesting thing, if you break your general s into real part and imaginary part, and you write this integral, and so this is e to the minus s become e to the minus sigma plus j omega. Then you can break it into the imaginary part and the real part, right? So imaginary part, you put it outside e to the minus j omega t. Then you can put this e to the minus sigma omega to your x of t together. And then you look at this thing, and you find out that this is a Fourier transform of x over t to the minus sigma t. Okay. So you can basically compute Laplace transform by doing Fourier transform to a different function. You just multiply your input function, not input, your function, your signal. You multiply your signal with HY exponential e to the minus sigma t. Then you do Fourier transform this, and that's your Laplace transform. Okay. So yeah. So you kind of think Laplace transform as different strips, right? So you think about a complex plane. Let me try to sketch. Hopefully this intuition is useful. So we kind of think about the complex plane. So the x-axis is sigma, and y-axis is j omega. And on the sigma equal to 0 axis of big X, so you can think about big X, So on the sigma equal to 0 axis is the Fourier transform. And for different omega, for different sigma, you have this different strip of e to the minus sigma t, and they will correspond to the Fourier transform of those different x of e to the minus sigma t. And so that's interesting. But what's more interesting thing is, so this sounds like a bad thing, but it's a very good thing that is x of s doesn't converge sometimes. Okay. And yeah, so we're going to be some region of x converge and some don't, and actually tells you a lot about your function. Okay. So it's best to see this in an example. So this is kind of our favorite signal of exponential decay. So xot equal to e to the minus at, and cut off at t equals 0 by this u of t. And we know it's Fourier transform. Yeah, so we know it's Fourier transform by do the integral, and this is 1 over j omega plus a, and the Fourier transform only converge when a is bigger than 0, because you want this to be absolutely integrable. Okay. So Fourier transform is this thing, and you can similarly do Laplace transform. So you put this in the equation. So big x of s is equal to your function, this thing, and times this e to the minus st, then you integrate by t. And then you can, just as here, you use this u of t to cut your t at 0. And is minus a and minus s can get together, become minus s plus a. And now you can break into part of you can break u the s equal into the real part and the imaginary part. So then you break this exponential into the real part and imaginary part, because here we assume a is something. Yeah, we assume a is real. Actually not. Okay. So a can be complex, so this might still be complex, but whatever. But anyway, so we compare this thing with our Fourier transform here, and we see that it's very similar to this equation, just instead of a here, we have sigma plus a here. And okay. Yeah, so instead of a here, we have sigma plus a here. And so we can also write this. So we can also get this integral as this thing. We just replace a with sigma plus a. And yeah, so we got this result. And it's a little weird. So we should say real a bigger than 0 here. Okay. And we have real sigma plus real a bigger than 0 here. I guess we are assuming a is real here, but a can be complex. Yeah, doesn't really matter. Yeah, so the presentation here is a is real. Okay. And anyway, so we replace a with sigma plus a here, and we want this thing to converge. Then we need that sigma plus a is bigger than 0. And you can move things a little around. And you combine the sigma and the plus 0 omega back to s, and the sigma plus a bigger than 0 thing. Okay, this is slightly just a very small part. So we want the real of this thing because it's weird when they are complex. So we want the real of this thing to be bigger than 0. Okay, and yeah, so you sort things out, and you will find out the real part of S. I guess it's real. That's stupid. Never mind. So both of the things are real here. Okay. So anyway, yeah, real part of S need to be bigger than -a because sigma is the real part of S. Okay. And anyway, so we found out the Laplace transform of this complex of this decaying exponential function is 1 over s plus a, and but we now have this weird part where this thing is only true for some of the s. This is only true if s is bigger than -a. If s is not bigger than -a, and then the integral just doesn't converge, and we think it's just not true. Okay. So yeah. So this is different from Fourier transform. Fourier transform, the convergence is kind of universal. How should I say? I should say it's kind of global because the transform is, we kind of think it's converge on some omega, then it's converge on omega. Or the other way, we say it's converged on some t, it's converged on OT. Even though sometimes with delta function, and we also think it's converged. But for Laplace transform, it's really different. This is very common. It actually happens most of the time that your Laplace transform only converge on some region. And this is going to be an important information of your Laplace transform. Yeah. So any questions so far about the Laplace transform of this decaying exponential? 1 over s plus a, but it's only true for the s that's bigger than -a. Okay. And you can plug in an exponential for some a, so a equals 0, then your x is 1 over s, but that only happens when s is bigger than 0. Okay. And you can also get back to the Fourier transform. So this is only convergent if RES is bigger than A, and in particular, if you want to get back to a Fourier transform, then you want A to be positive. So you can, so this thing is convergence on the imaginary axis here. And in that case, you will get back to your big X of j omega equal to 1 over j omega plus A. And we have 2 minutes. That's probably not enough for this. So let's stop here for now. Any question? Let's have a break. And yeah, let's have a break, and in the next session we'll see a very weird thing about another exponential function. Okay. Oh, sorry, there was a question here on even. Laplace transform 物理一可能就比较难看出来，有点现在我们的讲法比较像是一样是从时域走到频率，但是我们现在的频率是个 complex numbers， 现在有点像是 complex generalization of Fourier transform。就是我们现在我们的 frequency 是个很诡异的 complex number， 就本来的 Fourier transform 是这里是 E2的 J omega，但是我们现在 E2的 J omega 变成了这个 A4是 sigma plus J omega，所以我们等于是对，我们等于是我们的 frequency 多了一个 imaginary part 的 component，因为本来应该要 pure imaginary 的，多了 real 就等于多了一些虚数的 frequency。听起来是个很蠢的事情，但是实际上是很有用的。我们接下来会发现，你会发现，因为加了这些虚数的 frequency，然后它有时候不 converge，但是这个其实是好事。你看它到底 converge 的情况怎样，会告诉你方学很多事情。然后拿来解微分方程也蛮有用的。大概这样，对吧？你的确是会找 singular point。OK， 这样回答吗？OK，那我们先休息一下，把它改起来。 对啊，算是这样。乘上这个 e2 的 st 函数，然后再把 t 积分掉，你就会变出一个 s 函数出来嘛。哦，虽然说这里是乘以负 st 啊，不过其实差不多。Okay. Anyway, so this is the Fourier transform of e to the minus at, and this pair is going to be useful for this pair is going to be useful for a lot of calculation, as you can probably guess. When you solve differential equation, you are going to use them, just as when we do solve differential equation with Fourier transform, because complex these exponential decay are nice functions. Anyway, so we found out that exponential decay is very similar to Fourier transform. So instead of j omega, you have the s here, but it only converges on certain s. You need the real part of s to be bigger than minus a. Okay, now we look at a very interesting function. Okay, so we want to look at this function to compare it to the previous result. We now have a function that's also exponential decay, but in negative time. So I still have exponential, but now your u is not u of t, you have u minus t. So the cutoff of t equals 0, but you only take negative t. And so a, I think we also pick a is real here. But you want to decay in the negative time, so is a better be negative. And so this thing will converge. Anyway, so that's the form of this function, and the minus sign you will see why later. And then you can just brute force to computation and compute your Laplace transform. So once again, your function times is equal to minus st, then you do integration. And u will cut your t at 0, and once again, you have this exponent, you can combine them, so minus h plus a dt. And yeah, you can do this integration, although there are some complex number, but you can basically just treat them as there is no complex number. So you get 1 over h plus a. Okay. And okay, so 1 over h plus a, and so at 0 is 1, and at minus infinity will be 0. And but now we also need to check convergence. And for this thing to be convergent, you want it to decay in the negative time, right? So you want the real part of this number to be less than 0. And that just means the real part of s is less than negative a. So we also have the Fourier transform pair that, or this function, e to the minus at u minus t, and it Laplace transform to 1 over s plus a, and it's convergent on real s less than minus a. But now this looks a little weird, right? Because compared to what we just talked about last section, we have this exponential decay in positive time, and it also transforms to 1 over s plus a. Just the region of convergence is different. It's convergent on the big real s part. Okay? And yeah, so let's kind of see this side by side. So we have some a positive. Then we have two functions that in time domain looks very different. Right? In time domain, this thing only has things at positive time, and this thing only have strength in a negative time. And and also for positive a, this is for positive a, like we draw here. This thing is some divergent. It should not have Fourier transform, but it still can have Laplace transform. Okay, so even for a very divergent function, so for some a bigger than 0, it's going to infinity at t negative infinity, but you can still have convergent Laplace transform. You don't need to pick a very negative s here. Okay, it's very funny. And anyway, what we really want to say here is that so those very different functions, they have the same Laplace transform in the form of equation. They are both 1 over s plus a, 1 over s plus a. And their only difference is they have different region of convergence. Okay. So this function, when you do Laplace transform, you only convergent on the part of s that is bigger, where the real part of s is bigger than minus a. And for this function, when you do Laplace transform, you only convergent on those s, that the real part is less than negative a. And yeah, so this is a very important concept here. The important concept here is that when you do Laplace transform, you cannot just, so this, just writing this 1 over s a, this formula here is not enough. This region of convergence, so on which part of the S-plane this thing is convergent, it also gives you a lot of information about what your original function is. You see, those two things have the same expression here, but they have different region of convergence, and that gives them different function on time domain. And so when you write down the Laplace transform of some function, you always need to specify the region of convergence. Okay, I'll stop here for a second because it's really important. And also, if anyone has any question? No? Yeah, let's say this once again. When you write down the Laplace transform, the region of convergence, which is so important, we call it ROC, is an important part of the information of your Laplace transform, and you always need to write your region of convergence. And yeah, we will spend probably the rest of this section and some of the next section talking about things of the region, like talking about properties of those region of convergence. Okay, and anyway, so let's go through another example. And now we have a little more complicated example. That's the linear combination of two of those exponential decay. So it's like 9.1 with linear combination. Remember, 9.1 is this thing. Okay, so we now have two of them, and so the integration part is obviously linear, and so the Laplace transform is pretty linear in terms of the formula part, and you can basically just read here. So kind of skip the middle part and just read that. So this thing, the Laplace transform is going to be 1 raised plus 2, and you have 3, so you have 3 here, and also similar here. So minus 2, and this minus 1 become plus 1 here. So it's easy to write down this, but remember we need to specify the region of convergence. So what's the region of convergence for this thing? So when you want this integral to be convergent, then you want, okay, so this is not too rigorous, but basically you want, so this is sufficient, but also happen to be necessary. So you want those two integrals to be both convergent. Okay, and yeah, so you want the transform from here to convergent, and transform from here to convergent. And from what we talked about in the first example, so this Laplace transform is convergent on S bigger, real part of S bigger than -1, and this thing is convergent on real part of S bigger than -2. And you want both to be true, so you take the smaller of those two regions, that is bigger than -1. Okay. So yeah, so then that's our answer. Your Laplace transform is this thing, and with region of convergent on the smaller one, which is real S bigger than -1. And for reasons we're going to see later, we also want to multiply, do the cross multiplication out of this thing and read it in this rational form. Okay, you can also write this in rational form, just multiply things out. And so that's the Laplace transform of this linear combination of exponential. Any question? No? Okay. Yeah. So this just show you that you have two parts, and they have the separate region of convergence, and then you want to take the union of those things. So the smaller one, that's the bigger negative one. Will happen, the union happen to be the smaller one here. And now we can go to even more complicated example where now we have complex exponential. And yeah, we go complex exponential by get cosine here. Okay. So now our signal is once again real exponential decay, and another real exponential decay times this cosine function. So this is a real function, but we want to break into exponential, so let's get break into complex part. So once again, using the Euler formula, you break cosine equal to sine exponential, sine j something, and then sine minus j something. And combine with this minus t, then you get those two complex exponential. And then you do the Laplace transform of those complex exponential. And so even though on the example 9.1, we require, how should I say, we only derive for a real, but it's very obvious that it only works here. The 9.1 also works for a complex. Okay, and yeah. And yeah, you think about it, and it should also work for a complex, and you get a Laplace transform like this. So it's a here, then you get x plus a. So a equal to 2, so x plus a equals x plus 2, and a equal to 1 minus 3j, and you get x plus 1 minus 3j, and etc. 1 plus 3j and 1 plus 3j. And now what are the region convergence of those three things? So this thing we already know it should be real s bigger than negative 2. Well, the 2 here. And for those two things, you can very easily think about it. You can easily derive that when A is complex, you want the real part of S to be bigger than the negative of the real part of A. So the negative of the real part is 1 here. Okay. Any question? Okay. So those three functions, we have the 3 Laplace transform and corresponding 3 regional convergence. Now want the regional convergence of the whole thing, then you want the union of those 3 things. And you found out that the real is bigger than negative 1. Okay. And yeah, and for the formula part, you just write down the linear combination, and you have a 1 over 2 here, 1 over 2 here. So you get 1 over 2 to multiply here, 1 over 2 here. And you can also multiply everything out and get this rational function form. And yeah, so something here and dividing something. Any question? Okay. And now we can get some conclusion. And so what we have seen are very special examples of Laplace transform. So we always have those rational function of S, because for example here you see a polynomial S, excuse me, divided by another polynomial of S. Okay, and yeah, so a polynomial divided by another polynomial, that's called a rational function. And so rational functions are pretty nice, and for one, it's very easy to calculate their inverse Laplace transform. You can probably guess how you do the partial fraction expansion and try to get the inverse transform. Although they are regional convergence now, so it's more complicated. We will spend a significant portion of our analysis on the rational function. And although they are very special, we also see that a lot of things give you rational function. So for example, if your x of t, as we seen from the examples, if x of t is a linear combination of real complex exponential, then your x of s will be rational. Although if it's actually complex exponential, you might get some complex coefficient here, but that's okay. That's still rational as long as it's a polynomial s divided by a polynomial of s. Okay. And also, you probably can get this when we are solving differential equations, the linear constant coefficient differential equation, then you are going to get your system function as a rational function. And writing that as a rational function is actually very interesting for your differential equation, for your system function, because you can look at the polynomials, and polynomials you can find the roots, and the roots of n and the root of d will actually tell you a lot of property of your system. But that's something we're going to see later. But for now, we have something important here that we should probably say earlier. That is this name ROC. So so this ROC is as we have said orally, it stands for region of convergence, and it's a very important concept for Laplace transform. And yeah, and we are going to tell you more about it for the following. Okay, so any question for this example? So the linear combination of complex exponentials and their Laplace transform, which are rational functions, but with ROC being the union of all the ROC here. No question? Okay, then let's keep going. Let's see how far we can go. Okay, and so what we are going to do a lot is drawing pictures. So we kind of visualize the two examples we just had for the Laplace transform of the complex exponential. So the first one is linear combination is 3 and e to the minus 2, 2 minus 2 to the minus 1. And we have a Laplace transform is this rational function, and s minus 1 is squared plus 3s plus 2. And we can mark the root of the denominator, the root of the numerator and the root of the denominator. So this is a big N for numerator and a big D for denominator. Anyway, so the root of the numerator we will mark as a circle on our S-plane. So the root here is obviously 1. And the root of the denominator will mark as x. Okay. And mark as s on the S-plane. And they also, if you know, so now this is a concept from complex analysis. So you think about this function, then the circle part are the zeros of the function, right? So you plug s equal to 1, then this function becomes 0. And the closed part of s is going to be the poles of this function. So those are the value of s where this function becomes divergent. If you get a minus 1 here, then the denominator becomes 0, and this whole function goes to infinity. Okay. So yeah, so you mark the poles and the zeros of your Laplace transform on your S-plane, and they are going to be useful. And anyway, and you can see the region of convergence is this real s bigger than minus 1. Then minus 1 here is happen to be a pole, and region of convergence is this whole area. And similarly, for our linear combination of exponentials, complex exponential, then you also have the rational function. Now it's higher order, then you have lots of root. You have more roots and more poles. More roots for n and more roots for d. So roots here, we plot here. So the two complex number and the roots of those things is this -2 and -1 plus 3j, -1 minus 3j. Okay, so those -2 and -1 plus 3j, -1 minus 3j. And you see the region of convergence is everything right to those two poles. The rho s bigger than -1. Any question for those examples? And this picture of marking region of convergence and root and 0. And yeah, so this is going to happen in your homework and your exam. You are going to draw lots of this picture, draw the region of convergence and mark the roots and mark the zeros. And also just something for completeness. And so I guess in terms of mathematics, sometimes you will also think infinity as a point of your plan, and there can be zeros or poles at infinity. And so if infinity is 0, it means that reverse order. Okay, let's say the infinity is a pole, means that this function goes to infinity when it goes to infinity. And that means that this big N has higher order than big D. Okay? So if the order of N is more than order of D by K, then we think you have K's pole at the infinity. And on the other way around, if the order of D is more than order of N, then as S goes to infinity, this big X function goes to 0, and it's actually K's order 0 and infinity. Any question? No. Okay. So this is something complex analysis, but hopefully even if you haven't taken it, it's not too weird to you. Okay, then let's go to more example. And now now this example is a little more complicated. So we still have those two exponential function, but now we also have this delta function, and we want to do the Laplace transform. And those two things we have seen quite a bit of time, and they are going to give you this 1 over s plus a thing. And we can think about what's the what's the Laplace transform of delta function. Then we can do this post force calculation. So minus infinity to infinity delta t equals minus st dt. But delta function has this nice shifting property that it just puts pick out t equal to 0. Then you have e to the minus 0 going to be, no matter what the s of it, s times 0 is 0. So you get e to the minus 0 and it's just 1. Okay. So Laplace transform of the delta function is just 1, and this thing is true for any s. So now the region of convergence is something very nice. The region of convergence is the whole S plane. And then you can combine with the Laplace transform of those two things. And you can write all big X as just written now. So this become 1 as we calculated. Then you have these coefficients with your S plus A here. And the region convergence, once again, is the union of everything. And the union of those two will become RES bigger than 2. And the region of convergence is delta is everything. So it didn't give you any more restriction. So the region of convergence is just RES bigger than 2 from this -2 here, because you have sigma bigger than -1 here and sigma bigger than 2 here, and the 2 is the stricter one. Any question? And okay. And once again, we can write this as the rational function here. And is bigger than 2. And as we say, we like to draw those pole zero plot. So the poles of this thing is 1 pole is -1 and 1 pole is 2. So 1 pole is -1 and 1 pole is 2. And as we write down its rational form is s-1 squared here. So there's 2 poles at 1. Sorry, 2 zeros at 1. So you draw a double circle here. And once again, regional convergence is everything bigger than 2. Everything with real part bigger than 2. So all those things here. And okay. And also there is nothing at infinity because the degree is 2 here and the degree 2 is 2 down here. Question? Okay. And we get quite a bit of time, so we can probably finish this. So now let's talk about regional convergence. Hopefully it's intuitive because from what we have seen. So the first property is the most important property. So the region of convergence is going to be consisted of strips parallel to j omega axis in the x-plane. Okay. So although we already see head plane, so we're also seeing the head plane as strips. Okay. Anyway, by strip we basically means that. Okay, let's draw in. By strip we means that if some point is in the region of convergence, then the whole line with the same real part. So if you change the omega to everything, it will all be convergent. Okay. So some point is convergent, then you change the omega, it's all convergent. It's kind of because, like we said, the convergence of Fourier series, Fourier transform is global. So its point has convergent Fourier transform, then it's convergent for every omega. And yeah, and just as I said, remember, okay, remember sigma and j omega. Remember that the Laplace transform is the Fourier transform of this function x of t times e to the minus sigma t. And now we skip over a lot of details. So this bookmark here says that if you want more details, you should look up the math book. But here we only state the result. So for some sigma, so we already say is the region of convergence is going to be stripped. So for some sigma is convergent, is going to be convergent for that sigma and every omega. And whether that sigma is convergent is that it's basically whether this function has a Fourier transform. And the Fourier transform is convergent. We basically use the Dirichlet condition here. So it's convergent only if this thing is absolutely integrable. So the integration means infinity to infinity and absolute value of x, and e to minus sigma t already real, so we don't need to take already real positive, so we don't need to take absolute value some. So the integration x and e to minus sigma t dt, it need to be a finite value. then we think the whole strip here, the whole line with some sigma, will be in the ROC if this thing is finite. And this makes some sense because if you remember, you think about the Fourier transform of this thing, and this is exactly the first Dirichlet condition for these functions Fourier transform to be convergent. But okay, and let's go a little bit into the part we ignore. But this, if you think about the Dirichlet condition, there are actually 3 of them. And this condition only tells you that the first one is satisfied. And yeah, so what if the other 2 doesn't satisfy? I think we just think our function are nicely enough that the other 2 will also satisfy. But anyway, if you want more details, you can look at the book and you have the reference on this footnote, and you can study the details of the convergence of Laplace transform. And for now, we just use this easier condition that the corresponding Fourier transform function being absolutely integrable. It's x of t e to the minus sigma t being absolutely integrable, then we think this sigma strip is inside ROC. So, any question on this very important phase property? You can also think this kind of makes sense from thinking about the exponential functions we have been integrating. Okay, so we spent a lot of time talking about this. Now let's look at easier property. Okay, property number 2. If you have a rational Laplace transform, then that means that your big X is a rational function, so it has some poles and zeros. Then the ROC doesn't contain poles. And that's kind of obvious because at poles, X always goes to infinity, and obviously that's not convergent. Okay, yeah, that's just it. So your ROC need to avoid poles. So like in the example we have seen here, we have dashed line here. Remember? See? So it's dashed line here and it's bigger than 2. It's bigger than it's not bigger or equal to. So it technically doesn't contain this point because it's the open boundary here. Okay? So you can kind of clip the poles with the open boundary, but it doesn't contain the pole. And then now we go to some special functions. So I think we will skip the derivation because it's not too. Okay, let's see this. So if a function is really nice, if a function in a time domain x of t is finite duration and absolutely integrable, then it's so nice that your Laplace transform will converge everywhere. Then ROC is the entire plane. And what do we mean by finite duration and absolutely integrable? You kind of look at this. Although it can go to infinity as long as the integration is finite. Okay. So finite duration means that there is some starting time t1 and some ending time t2. And both of them are finite value, and your x of t only has value between those t1 and t2. So all 0 outside here. And it's also absolutely integrable, so you take absolute value and integrate anything, it should give you a finite value. Okay. And if your function is so nice, then your Laplace transform will converge everywhere. And it's just very easy to see intuitively. So your Laplace transform, I guess you check this property, right? So your Laplace transform is convergent if this thing is this x of t to the minus sigma t is absolutely integrable. So you will have x of t already here, and you are just multiplying it with another e to the minus sigma t. And your sigma might be positive, might be negative. So if the sigma is positive, you are multiplying a decaying exponential. And if it's positive, you are multiplying a growing exponential. But if your x of t is already absolutely integrable, then multiplying those exponential is going to be still absolutely integrable. Because, yeah, it's just a finite region. So multiplying this exponential is less than just multiplying this point. And multiplying this exponential is just less than just multiplying a constant over the exponential on this point. So that doesn't really change. And if you want to see the equations, you can calculate it out and you see that it's same as multiplying the exponential at some point. Yeah. And yeah. So it's pretty easy to think intuitive that those things are going to converge for any exponential here, just because they have finite duration and the exponential will have a finite value between them. And let's keep going through the equations because it's pretty easy. Yeah. So any question? So if your function is very nice, or signal is very nice, then you are going to converge everywhere. Okay? No? Okay. And okay, let's have an example here. So it's a very nice function. Actually, kind of similar. So it's still this exponential decay function, e to the minus at. Or it might not be decay because we didn't say it's positive or negative. But we cut it at the finite region. So it's between 0 and some big T. And we cut it between this region and it's 0 at all other place. And we can calculate the Laplace transform by falsely plugging the formula. So integration x of t e to the minus st, and already change the region to the integration boundary here. And you can work out the math, and you get this 1 over s plus a and the boundary point. Okay. And yeah, then because this has finite length, so your big X, so by our property, this thing should converge everywhere. Okay. And as we said, so this thing has to converge everywhere. And but this looks a little weird because you still have this 1 over s plus a, right? So you kind of have a pole here. You think, what if s equal to minus a, then this equal to infinity, and you get big trouble. If you go s equal to minus a is equal to infinity, then this x of big X should not converge. And that's actually okay because when s go to a, then it becomes 0, but this part also becomes 0, and you get 1 minus 1. So you have actually have a 0 divided by 0. We got wrong here. Okay, let me mark the and anyway, yeah, so you have 0 divided by 0, and by calculus you can actually see we can get the limit value of this by using L'Hopital rule. So you want to see what this thing is at, what's the value of this thing at s equal to minus a, then we just take its limiting value. It's technically a little bad, but we do it anyway. So yeah, we take the differentiation of the upper part and the differentiation of the lower part. Then you found out the differentiation is 1 here, and differentiation here is so -1, and you get negative t here. Okay. So you get negative t, and the whole thing, c to the minus at, e to the minus st. Yeah. And then you take s equal to minus a, so thing cancel out, you get this t out. So you see you have a finite value, or so you see x of s has some finite value big T here at s equal to minus a. So as we want, this thing is convergent on every s, because even on s equal to minus a, we can take the value of the limit being in T. So question on this property: if your function is really nice with a finite duration and absolutely integrable, then your region of convergence is going to be everywhere. No? Okay. Let's keep going. Let's see how many property. You can probably do a lot. And now if your function is only half nice, so it's right-sided, which means like this. So you only had the boundary on one side. Right-sided means that it might extend to a right to infinity. So when we say right-sided, it's more like it's left-bounded. Okay, so it has a boundary on the left side. At some point t1 is going to be 0 when you go to a negative, but on the right it can be anything. So right-sided function, then you can also get some restriction on your ROC. Now this, your ROC is going to be extended to the right all the way. So we write that in a weird little convoluted way. So we say that if some point is in ROC, then every point to the right of it is also in the ROC. So I guess a good example to remember this is when your x of t is exponential decay, right? The first example we see. So if x of t is just exponential decay, then remember your ROC is everything bigger than so the real part, everything with sigma bigger than minus a. Okay. And yeah, so that fits this description here. So if any point in ROC, then the point to the right are also in ROC. So your ROC just extend to the right to infinity. And yeah, and the proof is also quite intuitive. So you can already see here. So once again, we want to check this whether x times e to the minus sigma t is absolutely integrable. And now if a function looks like this, and x times e to the minus sigma t is integrable, so for some function sigma 0, then you change to, now you push to the right, means that you go to another sigma that's bigger. So you are multiplying your exponential that decaying faster, then you can only converge more, right? Because they have a cut point here, so this part is bigger, but whatever is going to be a constant vector, and whatever bad thing might happen in the infinite tail here, because your decaying is faster, it's going to be more convergent. That's very intuitive, and you can and you can check those with the equation here and prove that's true. So we can only look at the intuition here, that is convergent. So this x of t times e to the minus sigma t is convergent for some sigma 0. Then you go to some bigger sigma 1, then it's going to be, this exponential is going to be decaying faster. So all the bad thing happening in the tail here is going to get better. and it's going to be more convergent. Question about the property on right-sided function. No. Then okay. Then let's go to another property. So left-sided function. So we basically just switch left and right. So not too much to be said. Left-sided function is your function more like right bounded. You have a boundary on right. Stopping is on T2 or the T bigger than T2, your x of t going to be 0, and it can be anything on the left. And once again, the ROC is going to be on the right side. So this is like our second example, right? So in our second example, with like a function of decay in the negative exponential, then we have that our ROC is something go to the left. Is everything with sigma is there minus a, right? So more formal way to say this is that whenever a point is in ROC, or the point in the left of it is also in ROC. And the proof is similar. Okay, so we actually don't have picture here. But yeah, it's just changes left and right. So that's skip that. And then let's see is any question on the left-sided and right-sided function, and whether ROC are going to be half planes, going to extend all the way to the right or extend all the way to the left. So basically half planes. Okay. The next property here it says ROC are going to be okay. So now if x of t is two-sided, so basically nothing x of t is something general, then your ROC is going to be a strip. And so why is this surprising? It's actually pretty surprising that, so the important thing here is this A here. Okay, a strip means that there is only one strip. Okay. So from all the property we were talking about, actually only one property. So we're talking about ROC going to be stripped from the first property, right? So for two-sided function, everything else we talk about doesn't apply. So but the first property says that the ROC are strips. So I think that there are 2, 3, 4 strips, or maybe even discontinuous, or even infinitely many, but that's not possible. ROC going to be only one strip from this property. Okay. Yeah. And okay, and it's one strip, and there's a weird thing saying that it's going to be one strip, and if there is a point, then your strip will contain that point. Kind of obvious. Yeah. But the real thing this property want to say is that for a general function, your ROC going to be only one strip. Okay. Yeah. And two-sided function is kind of this. And I guess it's a little weird. But it's basically a general function, but we say it's infinitely extend to minus infinity to plus infinity. Anyway, so the derivation here is that we can break our x over t equal into so this two-sided function. We break into well over time, but it's really quick. So we break it into left-sided function and right-sided function. So we think this function is summation of those two functions, linear combination. Then the Laplace transform is going to be a linear combination of the transform of those two, and more importantly, the ROC, as we say, should be the union of the ROC of those two. And the ROC of this one should look like this, and the ROC of this one should look like that. and you take a union, then it's going to look like one street. Okay. So any question? And there's an example we don't have time to go over, but if any question, if not, I'll stop here. Okay? No? Okay. Then let's stop. Oh, yeah, question. 胡兆宏，有什么问题吗？
老师，请问听得到吗？
抱歉，你说什么？
老师，请问听得到吗？
可以，我还是没有听清楚。
老师，请问听得到吗？
听得到，听得到。
老师，我想问，那我可以从 ROC 去解释说，就是那个，就是我可以把拉普拉斯视为很多的 ROC 的像那个交集嘛？就是假设就是有两个，就是它是 linear combination 的话，我可以把两个式子视为就是那个就是两个 ROC 的交集嘛？
你有两个式子的话，照我们目前讲的话，是 ROC 就应该是所有东西 ROC 的交集，这是你要问的吗？
对老师，我可以视为就是他们的交界，就是或交集面积的重叠。
对对对。
好
因为照目前讲的，不知道会不会有奇怪，大部分应该对啦。虽然说，如果你真的要做很奇怪的例子的话，其实是有可能相消的。不过我们应该是不会做那么奇怪的事情。就是对啊，因为我们说我们希望是整个式子会 converge 嘛，所以希望是，比如说我们是想加的话，我看一下在哪，转。我们在什么时候讲的？对啊，例如说我们第一次来做这个东西的时候，我们是希望这个 part 要 converge， 这个 part 也要 converge， 所以就是这个 ROC 跟这个 ROC 的交集。但是你可以做个很蠢的 example 嘛，当然也有可能不是这样子。例如说你用个什么1倍的 e2 的负2t 跟负1倍的 e2 的负2t， 然后 x of t 真的是其实是0，然后所以 ROC 其实整个 plan 之类的。但是我们不会做这么奇怪的 example， 所以大致上可以看到 ROC 就是交集这样子。
好，那我大概了解。了解。
对。好，没有问题的话，蓝同学有什么问题吗？
老师，从 Laplace 找到那个 singular point 一定是 pole 吗？只能是 pole 吗？
只能是 pole 吗？听起来有点奇怪。说是 pole， 这样讲好像 singular point 只能是 pole 吗？应该 OK， 这副辩我不太记得。应该说，据我现在记得的，我们找到的应该都是 pole。可是你等于是说，你这样等于是在问说，一个 complex function 它会diverge的地方是不是都是 pole？
不是，
据我印象中的话，好像其实就是这样子吧。
Laplace 跟复变是有点关系啊。
Laplace 是傅立叶的 complex extension 啊，就是一开始我们讲的嘛，Laplace 的这个东西跟傅立叶的公式是一样的啊，只是本来这里 s 是要 strict on j omega 的，但是我们现在 s 可以是 any complex number， 就是一个我们应该要一直强调概念，就是这个 Laplace transform 你把它 constrain on 这个 purely imaginary axis 的话，你只看它在这里的话，那它就是 Fourier transform。对。那如果你 ROC 又包含这个 axis 的话，就代表你本来的 function 是可以做 Fourier transform 的，除了有些怪怪的事情。对，然后如果不包含的话，那就是没有 Fourier transform。大致上这样，虽然用那个 Dirichlet condition 很奇怪的事情。
OK， 好，谢谢老师。
对。OK， 没问题吧？那我们就结束。 结束。